Alright, here we go, chatting about gravity today. We've talked a lot about gravity in this class already, but we're kind of getting into the specifics here about the how and why behind gravity. There's actually a lot we still don't know, like as a scientific community, about gravity. A lot of it is still theory and theoretical, but there is still stuff that we know for sure that we're going to talk about today. So, the first thing we're going to talk about is the fact that gravity is a special type of force called a field. Now, a field is an area in which a force can act without touching the object. Most of the forces we talk about in this class are contact forces, where the object has to actually be touching the thing. In order for friction to occur, the object has to be touching something that produces that friction. Gravity is the exception to that rule. It says that gravity can act on an object without having to actually be in contact with it. Another thing we know for sure about gravity is that all objects with mass are gravitationally attracted to all other objects with mass. That's right. Every single thing with mass is gravitationally attracted to every other thing with mass. The reason we are gravitationally attracted to Earth is because it has so much mass that we're being pulled down towards it. If we were to take our whole class and stand out on a totally frictionless surface, after a while, we would eventually start to move together and clump up. Now, what we don't know very well about gravity is why mass produces gravity. We know that it does, we don't know quite why. There's two theories behind it right now, two main theories that people mostly talk about. The first one has to do with these subatomic particles called gravitons. Now, if we're talking about something like light, light has photons. Those are subatomic particles that transmit light. So here, for gravity, the theory is that there's essentially the same thing. These gravitons are these tiny particles that produce gravity, that when they interact with an object with mass, it causes the object to have a gravitational attraction to other objects. So we're kind of always walking around in these fields of gravitons without actually knowing it. Now, no one's actually discovered or detected gravitons before. It's still very theoretical, but it is one of the main theories when talking about gravity. The other comes from our pal Einstein and looks kind of like this. The idea is that all of space and time are just this flat-out stretched fabric, like here. And that when you place an object in that fabric, if it has a lot of mass, it's going to bend that fabric down. See how it's created this dent here with the sun? So, because space and time has been bent in that area, an object that is near the sun will be gravitationally attracted, right? It'll start to move down towards the sun. And so the more massive your object is, like a white dwarf is a more massive star than our sun, it's going to be more gravitationally attracted. There's more of a slope there towards the center. And then so on and so forth. Here is an example of a black hole that kind of breaks down a lot of our theories of gravity and mass and things like that, because it's such a massive object that it actually pops a hole straight through space-time, and we don't really know what's on the other side. So those are the leading theories on why gravity is, like why mass has gravity. No one really knows what the correct answer is. People are always looking to try and figure out the answer, though. Okay, let's talk about the math behind gravity. So far, we've mostly been using this equation for gravity, but there is a more accurate equation for gravity that we can find. Now, in the lab you guys did last week, you were testing a couple things. The first thing you were testing was how does the mass of the object affect the force of gravity acting on it? And you found that it was a linear relationship. There was a linear relationship between the amount of mass and the gravity, the force of gravity that acted on the object. Okay. We also found that if we changed the mass of the object on the left, it had the same effect. Sorry, let me draw that better. It had the same relationship as if we changed the mass on the right. So what does that tell us? That tells us that when solving for gravity, the mass of both objects should be considered. So there's m1 and there's m2. The other thing that you guys tested was how does the radius, or the distance between the two objects, affect the force of gravity acting on it. And you found that it had what we call an inverse square relationship. It looks like this. So in our equation, that's going to look like this. The distance between the two objects, the radius, has an inverse square relationship with force of gravity. Now there's one thing left that we have to add to this, because this equation right now is unbalanced. We have, in terms of units, we have kilograms squared on top and meters squared on bottom. But over here we have newtons, and a kilogram squared over meter squared is not a newton. So we have to put in some sort of constant to balance things out. We're going to use this here, big G. Big G stands for something called the universal gravitational constant. That is a number that will never change. As the name suggests, it's a constant. And it looks like this. Big G is equal to 6.67 times 10 to the negative 11. And the units are newtons meters squared divided by kilograms squared. So there you go. We are always going to have G, and this here is our final. This is a more accurate equation for force of gravity. Okay? Now, this equation still works up here in the top left. That is still accurate, but it is only accurate when we are on Earth's surface. And now that we have this equation here, we can leave Earth's surface and consider other planets and things out in space and stuff like that. Now, another thing that we can learn from this equation is we can actually build another equation that'll help us out. And it looks like this. If we were to set these two equal to each other, we would say mg equals big G, m1, m2, r squared. So in this case, this m would be the mass of whatever object we're trying to figure out the force of gravity on. So those actually are going to cancel out between these two. And we're going to be left with this helpful equation here. This is going to help us calculate the acceleration due to gravity on different planets. So acceleration due to gravity on Earth is 9.8, but elsewhere it's going to be different. So the equation there is going to be big G, or the universal gravitational constant, times the mass of the planet divided by the radius of the planet squared. All right? So this here is kind of our list of helpful equations for right now. Let me see if I can... Yeah, I'll just leave that there. So this is our list of helpful equations right here. All right, let's test this one out. Let's take Saturn, for instance. Saturn looks like this. It's the one with the rings. There you go. There's Saturn. We're going to try and find the acceleration due to gravity on Saturn. So we have acceleration due to gravity equals big G times mass over radius squared. So to solve, we have 6.67 times 10 to the negative 11th times the mass is 5.6 times 10 to the 26th. And then we have the radius is 3.6 times 10 to the 7th. And that, sorry, drawing of Saturn, you're going to have to move a little bit. Okay. And that there is going to be squared. You got to remember to square that. I think a lot of people make errors in their calculations, and it often comes down to forgetting to square that. So I'm going to plug this into my calculator here, and we're going to see what the acceleration due to gravity on Saturn is. Okay, so the answer I got here is 28.8 meters per second squared. So that is about 3 times as strong as planet Earth. So Saturn has got quite a force of gravity that it would act upon you. Okay, so there you go. Those are our basics for gravitation. This is what you're going to need to know for the test that is coming up. So yeah, hope this was helpful, and I'll see you guys later.